In this problem, we have two logs, W1 and W2, or I will refer to them as left and right logs, connected by a rope. They rest on a slope. The contacts have friction, and the friction is the same. And there are three contacts between the left log and the slope, the right leg and the slope, and at the peak of the slope, which is rounded where the rope makes a turn. I assume that there is no contact between the rope and the slope along the straight edges. Given the coefficient of friction mu, we need to find the range of weights W1 and W2 so that the logs are in equilibrium. We also would like to evaluate this answer numerically for mu equal to 0.2. I begin solving the problem by assuming that the situation is such that the left log moves down and the right log moves up. Actually, this is impending motion. I still consider that the logs are in equilibrium, but if this equilibrium is somehow disturbed, that would be the impending motion. Down, up. Now, here I have two free body diagrams. These free body diagrams are consistent with the adopted scenario in the sense that the forces F1 and F2 are directed against the motion. The slope angles are chosen such that the angle at the peak is equal to 90 degrees, and therefore the projections of the forces involved in these two free body diagrams are pretty straightforward and somewhat related. Next, I would like to consider the friction conditions. First, I will start with the rounded peak, and in a variety of ways we can convince ourselves that the contact angle is 90 degrees or P over 2. One way you may think about it is that when we went from this part of the slope to this part of the slope, we made a 90-degree turn. At any rate, for the adopted scenario, the force T1 should be larger than the force T2. Or alternatively, we can think about that in the adopted regime, the left log, W1, is stronger than the right log, and therefore the friction at this contact helps the weaker log. As a result, the condition for the impending motion is written in this form, where of course T1 is larger than T2. The conditions for the impending motion for the contacts between the logs and the slope are written in the usual form, and now we can put together equilibrium and friction conditions to do the following algebra. First, we solve the equilibrium equations for the normal forces N1 and N2. Then I will use the friction conditions between the logs and the slope to determine the friction forces. Then I will use the remaining equilibrium equations to determine the tensions T1 and T2. They are now expressed in terms of the weights W1 and W2. Then I calculate the ratio of the tensions, and I know that on one hand, from the friction condition, it is exponentially expressed, but also from these two equations, I have this condition, And now I can solve this equation for the ratio W1 to W2. I obtain this expression, and for mu equal to 0.2, the ratio is 4.05. So what this means is the following, that if the weight of the left log, W1, is larger than 405 weights of the right log, or W2, then the two logs will be moving in the regime that we assumed. In other words, the left log goes down and the right log goes up. Now let us explore another regime where the right log takes an upper hand and its impending motion is down, and the left log state of impending motion is up. Now I have to change the direction of the friction forces in comparison to the regime 1, and these directions are consistent with the right log going down and the left log going up. The equilibrium equations, and now the friction condition at the peak emphasizes that the force T2 must be larger than the force T1, because now the friction helps the left log. We go pretty much to the same algebra, and we obtain that the ratio of W1 to W2 in general is given by this expression. For mu equal to 0.2, the numerical answer is 0.831. Now I can summarize my analysis by showing the following diagram. Along the axis, I plot the ratio of W1 over W2 for mu equal to 0.2. And here we have the following situation. If the ratio of the weights, W1 to W2, is less than 0.83, then the right log takes an upper hand. So it moves down and the left log moves up. On the other hand, if the ratio of the weights is above 4.05, then the left log takes an upper hand and it moves down while the right log moves up. For all the weights with the ratio in between 0.83 and 4.05, we have a stalemate. The asymmetry in these values is not surprising, because the right log has a steeper slope, so it doesn't take as much for the right log to overcome the left log. On the other hand, for the left log to overcome, because its slope is not that steep, it needs to be significantly heavier than the right log. Thank you.